Hi everyone, thanks for checking out this video. So in this lesson, we're going to add another operation for our tensor type that we're working on. And this is what's called the ReLU activation function. So this is something that sounds like really confusing and sounds like it would be something complicated or difficult, but it's actually really simple. And this is a thing that's, sometimes you see in like machine learning and computer science and stuff like that, people will give complicated sounding names to things that are actually very simple. So this is a great example of that. So it stands for rectified linear unit, which again sounds like something confusing, but all it means is that when you apply the ReLU function, all it does is make negative numbers 0. So if you have a positive number, you just keep it the same, and if you have 0, then it stays 0, and if you have a negative number, you just make it 0. So sometimes the way it's written is like max of 0 and z, where z is the number that you're passing into the function, and this is how the plot of it looks. So on the positive side of 0, it's just a y equals x line where the output is the same as the input, and then on the negative side, whatever negative number you give it, it just becomes 0. And so it's a very simple activation function. There are some theoretical reasons why it's used. So the most basic explanation is that it adds nonlinearity into the model, similar to the tan h function that we wrote for our value type. That's another type of like nonlinear activation function. So that's the most basic reason, and then there's some other theoretical reasons why people use it. But yeah, those are a little bit beyond the scope of this video. So today I'm going to show you guys just how to write the forward and backward pass for this ReLU activation function for our tensor type that we're working on. Okay, and like usual, I just have our code so far at the top. I'm just going to run this code so we can use it. Okay. Now, I guess first I'll just show you guys like a little bit of like an example, just to, I know I just told you what it does, but basically what we want to happen is, let's say we just have some array called A, and we're going to write this to work for tensors, but to show you guys what it's supposed to do, I'll just use a regular array for now. So let's say we just have an array full of some numbers like 1.2, negative 5.4, 10.3, and negative 2.0. So the output is going to be something like basically something like max dot 0 a, and then we can print the output. And yeah, so all it does is it just makes the negative number 0, and any number that's non-negative, it just keeps it the same. So our negative numbers became 0, and the positive numbers stayed the same. So yeah, very, very simple, but this will allow us to add some non-linearity into our eventual neural network, which is kind of the point of it. Okay, so now let's work on writing this for our tensor type that we're working on. Okay, so like we've been doing, we're going to copy and paste some code, and just so we can have something to work with. So I'm going to copy and paste the tan h code, even though we're not doing tan h anymore. We're doing this new ReLU activation function rather than tan h. But I'm just going to use this code, just this code block as like a template to go off of. Okay, so first things first, we'll change the function name to just ReLU. It's only going to take one argument. It doesn't take in two tensors. It only takes one tensor as a input argument. So it's still going to just be A, but A is now going to be of type tensor. And then the output is going to be like we just did up here. It's going to be max dot 0 and A dot data. And remember, in Julia, this dot basically is used for element-wise operations in arrays. So this is saying, okay, for every element, we're going to take the max of that element and 0, basically. We're keeping the non-negative elements, and any negative elements are becoming 0, basically. Okay, and then we want to store our result like usual. It's going to be a tensor. The tensor.data is going to be out. And then we want to just grab our usual like zeros matrix we've been using here. So yeah, I'm kind of breezing through this. Hopefully you guys are getting used to this even for the tensors now, because we've done 2 videos on other tensor operations. But yeah, so this is just going to be the placeholder for the tensor.grad. So we're just making it an array full of zeros of type float64, and it's going to be the same size, meaning the same shape basically as the output, which in this case will be the same shape as A, because it doesn't change the shape at all. And then yeah, we're gonna make the operation just the same thing as this, except ReLU for the actual operation name. And then I'll just change this comment here too to make it tensor, just so that we can keep track of things. And then I'll delete this comment. So yeah, that's it for the forward pass. We also have to do the backward pass. For this one, the backward pass is actually pretty easy and pretty intuitive. So yeah, I'm actually just gonna grab just to copy and paste. Yeah, I'm just gonna grab the tan H back prop. Yeah, use this little template here. Okay, and then we just have to make our usual like small changes. So we'll make this tensor, and it's going to be type tensor. This operation typing here is the same, but it's going to be change tan H there to ReLU. Okay, and so this is a situation where we have tensor equals ReLU of A, and then our goal is to take in that, if we're passing that tensor into this backprop function, we're going to be updating a.grad. We basically do that the same way as we've been doing it. So again, sorry, I'm kind of breezing through this video, but yeah, we've done this even for tensors for two other operations already. So hopefully this is making sense to you guys. So we're gonna update a.grad by saying tensor.op.args, the first and only argument .grad. So that's like the a.grad here. And then here's the actual update. So it might look a little bit confusing at first, but I'll just type it out and then I'll tell you guys what it's doing basically. Tensor.op.args, first and only argument .data point 0 dot times tensor.grad. And okay, before we run this, I just want to show you guys, because this one's simple enough that I can somewhat easily explain it. So let's think about what this part is doing here. So let's just say that let's think about what this section of code is doing here, basically. So let's just say that we had some array that is like, you know what, we can use the same test that we did up here. And then let's just run this code and just see what it gives us. Yeah, so this just returns like a 1 or 0 like integer like Boolean representation, whether like depending on if it's true or not. And yeah, basically this is saying that, since remember, like when we're doing this function on A, all of the positive elements are staying positive, and all of the 0 or negative elements are going to be 0 in the output. So basically, anything that's negative or 0, the gradient will be updated by 0, meaning it won't be updated at all, because like if one of these was negative, that negative is just getting erased in this activation function. It's just becoming 0, so it's not actually impacting the final output at all. So that's the way to kind of wrap your head around what's happening here, is that these negatives are just becoming 0 as it goes through this activation function. So they're not actually having any impact on the final output. They're just becoming zeros basically. So it doesn't matter how negative they are. Basically like this -2 here would have the same impact on the final output as if it was a negative 1000, because the -2 and the -1000 here both would just become 0 as it goes through this ReLU function. So yeah, that's why the gradient is 0 in that case. It's just because making a small change to it basically doesn't impact the output. But if it's positive, then it becomes a 1, and that 1 allows the gradient to like flow back through those numbers, because they are impacting the final output, like based on small changes to them. A small change in one of these positive numbers would impact the output. So this like 1 and 0 is just telling us with the gradient whether a small change in these numbers would impact the final output or not. And the reason we're multiplying it by Tensor.Grad is because of the chain rule. Because this tensor that we're passing into this backprop might not be the final output. This might be something that we have to chain rule back, like we've been doing. So hopefully that makes sense to you guys. That's my attempt at a quick explanation. A little bit confusing. Yeah, if anything didn't make sense, I would encourage you to maybe like prove it to yourself with a couple examples yourself. But yeah, it's a little explanation. But yeah, so I think that's all the code we need for the backward pass. Yes, I'll just run this to save it. But yeah, like I've been telling you guys, we're not going to test these yet. We're going to write the operations for the tensors and then do like a final test at the end. So we're getting close. We're getting to that point pretty soon. After this video, there's one more function we need to do, and it actually is like the hardest function. So there's one more kind of difficult part left, and then we're going to be done, and we're going to finally put everything together into the actual neural network that I've been promising you guys this whole video series so far. So thank you everyone for being patient. I know it's taking a while to get to the neural networks, but I hope you guys see that we're like building up a foundation of like intuitive understanding here, so that when it comes time to actually write the neural network, we're just going to be putting together all of these pieces basically. But yes, that's all I have for you guys for this video. So thanks for watching, and see you next time.